the new audience who just joined the session, my name is Tan Sui. I'm Associate Professor or Reader from the University of Surrey, UK. But at the same time, I'm still holding the Royal Academy of Engineering Industrial Fellowship. Therefore, I'm under secondments with the National Physical Laboratory. So this fellowship is pretty much focused on the developments of the innovative residual stress evaluation approach for the application of the nuclear fusion and nuclear fusion industry. So by nature, this project has been in collaboration with the UK Atomic Energy Authority, which is the UKEA. All right, thank you. So the first question is really, what is the residual stress? Why we're being, so fascinated of studying, investigating the residual stress? So the residual stress is the stress remained in the object without even external load. So I often use the example from the biological tissues. One of the reasons is the other side of my research team is pretty much work on the biomaterials and the bio-inspired composite materials for dentistry. So as a biological tissues, system ourselves, we've pretty much been benefited of having the residual stress. For example, we have tensile residual stress for most of the soft tissues, like the skins, to remain this integrity, but at the same time, remain the functionality. And similarly, for the hard tissues, usually it has a layer of the compressive residual stress, which prevents the crack initiation and propagation. But now in the context of the engineering industry, the question is really, are we suffered from the detrimental residual stress? How are we going to cope with that? But first of all, we need to be able to develop the capability of measure those residual stress with good confidence, reliably, and could also be cost effectively. So that comes to the research focus is pretty much to build the capability in evaluating the detrimental residual stress. And the examples showing on the top right, showing how the detrimental residual stress can lead to the formation of the crack, propagation, distortion of the materials, components, and the system. As a result, those detrimental residual stress will significantly shorten the lifetime of the materials and system in service. So our approach is to start with step one of building the capability that requires the developments of the cutting edge technologies. For example, the neutron-based imaging, neutron-based diffraction techniques, which is very much complementary to the surface analysis techniques we've been focused on. And then move to the second step is really to build the understanding of those residual stress evaluation. So by doing this approach, we're able to quantify the residual stress in good confidence, but at the same time building the correlation with the residual stress, with the microstructure, but also the mechanical property and so on, for example, mechanical behavior. Moving to the third step, the insights from those experimental observations is really to help us to build, say, machine learning powered modeling or finite element-based modeling to be able to predict the residual stress, once again, cost effectively, reliably, and ultimately, we want to optimize the materials processing, manufacturing processing to reduce the amount of the detrimental residual stress. And therefore, we are working towards the extend the lifetime of the materials in service. But of course, here is primarily in the focus for the UK's first nuclear fusion reactor and the power plant. So this is pretty much, the previous slides showing pretty much a linear approach we've been taking to tackle the challenges of the residual stress. And if we can reshuffle, the methodologies, evaluation, modeling, and this is another way we can build our triangle in my research group, focused on the micromechanics, microstructure, and modeling. So on the left-hand side is pretty much the characterization capability in collaboration with a large-scale facility, such as the ISIS beamline, but also, other neutron-based beamline across the world. Those large-scale facility gives understanding in the bulk materials with moderate resolutions. But we also want to understand the residual stress and the microstructure in the much finer levels, and that requires the characterizations of using the surface analysis, such as the scanning electron microscopy, electron backscatter diffraction techniques. So those microstructure characterizations then directly contribute to the understanding of the residual stress and the residual stress evaluation. As you can tell, we are building the strategic partnership amongst Surrey, University of Surrey, UKEA, and NPL with the complementary capabilities. So the core of the surface analysis we've been building is around the plasma focusing beam at Surrey and being well supported with the in-situ and in-SEM capabilities such as the micromechanical tester, in-situ nano-indentation, etc. But we've been well supported with the high temperature nano-indentation capability at NPL, and also the capability of testing radioactive materials at the UKEA's user facility. So as mentioned, the observations, the comprehensive understanding of the residual stress with the supporting microstructure is going to contribute into the establishment of the fundamental modeling, machine learning powered approach. Ultimately, we are building a user-friendly interface that we want the industry to be more accessible into the residual stress evaluation. And if you look at the agenda on the day, you will find out after me is pretty much our group presentations. So the one next to me is Dr. Bing Zhu. So his talk is going to focus on the evaluation of using the large-scale facility, such as the broad gauge imaging, neutron diffraction, and the broad gauge imaging tomography techniques. David, and perhaps he gives the talk right after Bing. So we're going to support, David's talk with OMAS. So his research is pretty much focused on the developments of the VDIC, a plasma focusing beam digital image correlation method combined with the nano-indentation to evaluate the metallic joints, which he will talk about in bit details. So his work is pretty much also aligned with OMAS work, again, focused on the dissimilar joints evaluation, and all the experimental contribution will become the input and output of randomness machine learning models, which is going to talk about how to evaluate these analytical results to be a reliable model. So this is pretty much we've been focused on, and I'm pretty sure David's going to elaborate that in a bit more details. So my overview is like we are trying to build the capability which is more representative to the bulk behavior. That's why we've been developing the plasma focusing beam-based residual stress evaluation in contrast to the gallium focusing beam. We are looking for the high precision, also looking for the multi-scale capability. So essentially, we use the plasma focusing beam to remove the materials layer by layer with the hundreds nanometers precisions, and then use the scanning electron microscopy to capture the resulting displacements at the resolution of the pixel and the subpixels. At the time, the depth of the removal materials equals to diameter of the pillar. The residual strain has been fully relieved. At this point, this pillar can serve as a stress-free reference, and then we can apply the nano-indentation on top of the pillar. By making comparison of the stress-free pillar with the region of the interest, we'll be able to apply the nano-indentation to achieve fast, large areas of the residual stress maps. Not so sure this is going to work. So I think this video doesn't work, but it really showcases how we interpret the data to achieve the depth profiling of the residual stress of using nano-indentation techniques. So again, my talk pretty much gives an introductory overview about my research group on the nuclear fusion energy industry applications. So as you can tell, we've been working on different metallic joints, with the example on top is the EUROFER97, which is pretty much Dr. Bing Zhu's research focus. The one at the bottom is the dissimilar EUROFER97 with tungsten. That is the Davis research focus, and why brazing is so important of bringing two distinct materials instead of using, for example, laser welding for the EUROFER similar joints. So almost research is pretty much focused slightly different, material system, as it's contributing to a different components, which is called the diverter for the nuclear fusion reactor. So in these scenarios, it would be interesting understanding the effects of the high heat flux, how the recrystallization will induce the residual stress, but also it would be interesting to understand the residual stress distribution across 3 distinct layers, with the plasma-facing tungsten to the copper chrome zirconia with the interlayer of the copper. So Almost talk is going to discuss about 2 effects on the residual stress distribution in this monoblock. So in the past 2 years, as a group, we've been very productive. So here are some snapshots of our recent publications. The first one is really to combine the bright edge imaging to achieve the in-through thickness residual stress distribution with a moderate resolution, and how that has been combined with the neutron fraction to achieve depth-dependent residual strain distribution. So it will be able to create this pseudo 3D residual strain reconstruction. And this idea and this research findings really inspired us to move one step further, is to achieve the residual strain tomography by developing such techniques, which is called neutron bright edge imaging tomography, with the limited and projections to achieve the cost-effective approach on evaluating the residual strain in 3 dimensions. Through those observations, we observe very minimum variation through the thickness of the joints. So that further, inspired us to be focused on the surface analysis, which we want to build understanding from like a millimeter, hundreds microns resolution down to a few microns or even hundreds of nanometers. So this is pretty much the showcase of how we develop and successfully apply the combined plasma focused ion beam digital image correlation with the nano-indentation techniques in quantifying those residual stress. So with such success and confidence in evaluating the residual stress, we'll be moving on to the applications of the dissimilar joints. And there are lots of ongoing work, under the preparation, which demonstrates our research focus is really to commit to the residual stress quantification and the modeling, and eventually we hope we're able to optimize, as mentioned at the very beginning, optimize the materials processing and to minimize the detrimental residual stress. I think I'm pretty much on time. So this is really the last slides, being focused on the large-scale facility interactions in collaboration with the UKA has been well recognized by the neutron assets in terms of the economic contribution or economic impact contribution in the field.